So I have now obligated myself to give you the syntax, the structural equivalence, and the rewrite rules. So that's what I'll do. And by the way, when you are specifying something like Java, the rewrite rules are just the transition rules of the virtual machine, and that's something that is a dividing line for language design that we should talk about in this context, so that people understand some of the design desiderata here. Okay. So the syntax, I'm now giving you the core of Rholang, which is the row calculus. And then we're going to expand that core and talk about how we expand that core so that the compiler is always correct by construction. So I did this already once before, but so you guys can walk me through this already. Right? So what is it? Sweet. And okay, let's get something that gets us off the ground, something a little more atomic before the parallel.
You have sending and receiving.
Thank you. Yes. So here's sending. And then okay, and I'm going to do the one receive version, and then we'll talk about how you go from to the join version. So I have something over here that's an X, and I have something that's here that's an X, and then I get a P of X, and then now we can do your par. And then I can do a star X. Have I got them all? What?
That'll be the...
Yeah. And so, yeah. So the reflection is going to be, so we have to be able to do, so X we know has to satisfy an equation, right? The equation is X is going to be equal to something else, say X prime, plus P of X, right? And that's what supports this at P operation. So X's are of the form that plus something else. Right, so now let's just erase these because we're doing the reflective version. Right, and erase these, and now there. That's the reflective version.
No, because you need to replace all your X's by at P's. I mean, yeah,
no.
I guess you can close it up that way.
I closed it up that way, exactly. And then we just said that there's some other stuff as well, which we're leaving out for the time being. So that's our syntax. And now the structural equivalence is very easy. Is it possible to just... The shoes, maybe? Good idea. Thank you. And then coming back a little bit. Okay, so here's the structural equivalence. Okay, the first thing is, and these are all very, very intuitive. If I have a P and I run it in parallel with the stopped process, that really should be P. Yeah? If I have a P and I run it in parallel with Q, surely that's the same as running Q in parallel with P. Yeah? Cool. And then it should be the case that if I have, is everyone here familiar with free and bound? Free and bound. Yeah. Everyone here cool with free and bound?
There
Okay, all right. So in order to give structural equivalence completely, I need to tell you, so I'll do it as a where clause. So we'll in a minute, we'll talk about what free and bound means. But intuitively, to motivate that, I'll say that this expression binds this one. So if you permit me, y is bound in this expression. And so what that means is that if I do for y from x p, that this is structurally equivalent to for z from x. And now I'm going to introduce some notation, which is substitute z for y in p. So everywhere I have a y, substitute z for it. The caveat, and this is why I need free and bound, is that z can't have occurred bound in p. So I want to pick z to be fresh. It needs to be fresh with respect to p to be completely safe.
So can you just clarify what the first one is?
So basically doesn't occur.
Okay.
Yeah, that'll give you nice and safe. You don't get any collisions, right? So these are the same. And you all know this, right? If I wrote my C function foo, it's parametric in x. If I rewrite it to be parametric in y, it's the same function foo, yeah? Rockin', okay. And then there's only one other, and this is the tricky bit with row calculus. So far, the row calculus has fewer moving parts than the pi calculus, and way fewer moving parts than the higher order pi calculus. And yet, it's higher order because I get to send processes. So it's a significant improvement over both from a complexity standpoint so far. From a complexity standpoint so far, it's a significant improvement over the pi calculus because we get higher order behavior, and you'll see we get reflection, and we have far fewer moving parts, so it's easier to reason about. But there's some complexity that's been hiding under the carpet here, and that has to do with when do I know that two names are equal? So we actually have to formally define, because we have this weird thing here, we have to formally define name equality. Okay, so two names are going to be equal. So I'm going to ignore this because if you hand me any other names besides these, I'm just going to insist that there are at least countably many of them and you have an effective equality. Right? That's just my requirement if you hand me any other names here. So we'll just forget about these for the moment and talk about name equality with respect to those. And essentially, what we're going to insist is that if I have that P is structurally equivalent to Q, then it should be the case that at P is name equivalent to at Q. And then we use this name equivalence whenever we want to do things like substitution or other kinds of comparisons of names. But it's absolutely necessary when we're doing substitution, and when we get to the operational semantics, it's absolutely necessary because that's the workhorse of reaction, is being able to make this determination. Is that making sense? People tracking?
You said reaction. Do you mean as in reactive programming, or do you mean something else?
When an output meets an input,
That's the reaction.
that's the reaction, and it's so like a chemical reaction that you can literally model faithfully chemical reactions in this way by adding reaction rates to this and building stochastic versions of these calculi. So that turns out to be fantastic really interesting applications of this stuff to biology and other kinds of things. So there's one other thing that we need to worry about. I always get this backwards. So what you want to do is you want to say, if I started from a process, so hang on, if I start from a name, so this is the wrong way around. So if I start from a name and I dereference it, versus if I start from a process and I name it and then dereference it, right? So there's a couple of different ways we can go, right? And one of these ways you want to preserve things, right? So this one we don't like. Sorry. If I start here, start from a name, and I dereference it and I add that, this one we like. And that's good because we would like to be able to compare things that should effectively be data. But if I start from a process, I take a name and dereference it, this one we're not going to admit. Sorry. Because that puts too many constraints. Basically, you're introducing undecidability here into the calculus. Here, this is nice. So
at is a one side, is a left inverse for star,
yeah,
not the other way
yeah,
around.
exactly. So these are our two name equivalents, and now this is kind of important. So look, we've said that alpha equivalence, which is effectively this is really called alpha equivalence. So structural equivalence is the smallest equivalence that includes alpha equivalence and expands it with these equations. So that's structural equivalence. And now notice that alpha equivalence depends upon name equivalence, which depends upon structural equivalence, which depends upon alpha equivalence, right? So we've got a loop. And what you have to do to get off the ground is to say that there's a way to break the loop. And the way you break the loop, I don't know if anyone has spotted it yet, but there's a very strict discipline here. And the strict discipline is that we never double up, we never have two name constructors in a row. We never so you always have alternating name, process, name, process, name, process, right? So here I have a process. To go any further from this is my ground. To go any further, I have to have a name. There's nothing else here that allows me to make more processes. So I make a name like @0, right? And then I can make some more processes. Yes?
So when you say you can't make more processes, we've got 0 par 0, but that's structurally equivalent to 0.
Exactly.
And we never see any at or star star.
Never see any at or star star. Exactly right. So there's a strict discipline here, and so yes.
Oh, just one other mnemonic. You can think of at as being a derivative and star as an integral.
Yes.
And then that falls out. So a process is the fundamental thing, and a name is somehow one level lower.
Yeah. That's nice. That's very nice. So basically, what you end up doing is you can show that you go round the loop here, and you unwind until you get down to 0 equals 0, or that you don't have something like that. And at that point, you know that they're not equal. So that's how you show that the cycle terminates. Just for those people who are interested and want to be tantalized, the strict alternating discipline is closely and intentionally related to two-player games. So there's a game theoretic design hiding underneath this design. So think of at as player, process as player, and name as opponent. And the strict alternation here is part of a game. And we know that lots of these games terminate. If you get really interested, you can introduce non-terminating games, which are names that are fixed points of process definitions. Yes?
Just for those of us just catching up here, this is the reason that there's no at P production on the P side.
Correct. Because at P returns a name. Yeah.
Chris, can you repeat that? My question was whether this is the reason there's no at P production for P.
Right. Yeah, exactly. Yeah. There are two categories, processes and names, right? At P takes you from this category to this category. Star X takes you from this category to that category. So they're like that.
I have a question. I'm not sure I quite understand how the name equivalence loops into the alpha equivalence.
Right.
Are we maybe missing name equivalence of two names implies?
No, you can't do substitution.
When you're going to substitution, you're going, is this term equal to the one I'm looking for? Is this term equal to the one I'm looking for? Is this term equal to the one I'm looking for?
So if we could write that somewhat explicitly, then we would say the definition of that substitution involves name equivalence.
That's correct.
Okay.
Yep, that's right.
And just to clarify, there's no need for another equivalence that's like the opposite of the one in the lower left-hand corner,
Lower
but with
left-hand
stars,
corner?
right?
This
Like
one?
if I have name 1 is name equivalent to name 2, does that imply that star name 1 is equivalent to start name 2, or is that?
It's not a requirement of the calculus.
Okay.
There may be calculi where that's true. Okay, so I've been obligated to give you syntax and structural equivalence, and now I give you the operational semantics, and it fundamentally uses these things. Okay, so these are all so intuitive that I'm going to erase these unless there's objections. Sweet. Okay, so effectively, there's one workhorse engine in the whole calculus. So the workhorse engine, and this is the same as a rewrite for a virtual machine, and I'll get to that in just a minute. So what we want to say, and in deference to Robin, I tend to do it this way. And the reason is because this is like the generalization of abstraction. So one way to, for those people who are functional, think about here, they have to be in lexical proximity to each other, right, in order to do the application. Robin's idea is name the application site, and then they rendezvous at the application site, and then you do the application. Right? That was the whole trick for the development of the PyCalculus. So that's what we're doing. Here's the application site. Here's the abstraction, and in fact, you can find the abstraction. Remember, I said this is bound. Okay, so effectively, you can think of this as a y. If you give me a y, I'll give you back a p, right? And I'm hanging that off of an x, right? And the 4 is just syntactic sugar, and in fact, this is almost Robin's original notation, right? So just so people are aware, and if you go to the literature, which I strongly, strongly, strongly recommend for everybody, because this is, remember I said we have a lot of balls in the air, and if you just have this one ball in the air, that will drive everything. So strongly recommend going to the literature and becoming familiar with this. So this is the secret decoder ring for our notation versus Robin's notation. And we do this because we're exploiting the fact that if you go and look at the semantic models, these end up being certain kinds of monads. So we're just going to generalize the monads, and the for comprehension notation is a very convenient notation for a wide range of monads. So that's why I shifted from here to here, and as soon as I did that, it became apparent how we could introduce join. So. It's a kind of, it utilizes the monad multiplication. Good question. So in the concurrency literature, join means like fork join. So I've got a thread running and a thread running, and this thread can't go until I get the results of both of these, right? And so Cedric Fournet, with whom I worked at Microsoft, he recognized in the same way that I did that a lot of human decision-making processes and concurrency design patterns that are human relevant are all fork join. And PyCalculus sucks at fork join. Robin's original notation, like that. That is not conceptual. It doesn't lend you to the right way to extend the calculus to give you a join, right? So Cedric recarved up the calculus to give a join, but the way he carved it up wedded replication and a bunch of other things. A bunch of features all kind of got tangled up into one thing, and the semantics is not very good for the kinds of programs we want to write. When we do it this way, we get a very natural join that isn't tangled with anything. So.
Now, I can see two different possibilities for join there.
Yeah.
One is you say for y1 from x1 semicolon y2 from x2, that gets a y1 and a y2.
Uh-huh.
An alternate one is that it's more like a select, and you either get a y1 or a y2.
Yeah. We'll talk about that in a minute. Yeah, absolutely. Absolutely. And we went down a particular design option that's more general than that. So, yeah. Okay. So, so this goes to, they synchronize at x. We take, we turn Q into its name, so a data type that freezes Q up and makes it transmittable. And we pass it in and substitute it in for y everywhere it occurs in P. So this becomes P, in which we take the name of Q and substitute it in for y. So that's the workhorse of the calculus. There's hardly anything to it, yeah?
One other point that I guess we skipped over is that at effectively binds all of the names in Q, so that when you're doing substitution,
yeah,
you don't substitute under an at.
Yeah, that's correct. That's correct. So that's a subtlety that is addressed in the paper. So that basically there's a kind of syntactic substitution which is blind to all of that, and a semantic substitution which is sensitive to that. And so that's, if you want the details of that, just go look at the paper. It's not particularly hard. Okay, so then the only other thing we want to do is we want to say, in which code context can we apply this rule? Like, for example, if P were a par, could I reduce under a send? Like, could this thing be wiggling while it's waiting around to be sent? Right? That's one possibility, right? We're going to eliminate or exclude that possibility. Can this P be reducing while waiting for input? That's a possibility, right? We could let that happen. This doesn't really say much about the code context in which that wiggling can happen. You're furrowing your brow and shaking your head.
I don't know what wiggling is, right? In the PyCalculus, it could have been reducing if P were an adjunction of input and output guards that were meeting, right?
No. The question is nested contexts. So in the PyCalculus, there's a restricted set of nested contexts where you can reduce, where you can apply this rule. So here I'll write the context out, and
Greg?
you'll see. Yes.
Just to make it explicit, the question is, if P par Q reduces all by itself, is it also the case that for y from x, P par Q also reduces, or not? Is it the case that x bang P par Q reduces? And so that's
Yeah.
the question he's addressing here.
Yeah, exactly. And that's what I mean by wiggling. Can I apply the COM rule in some nested context? Right? Right? And we give explicit answers. So we say there's exactly one place where this can happen. So if P reduces to P prime, then we get that P par Q reduces to P prime par Q. And then the last rule is a rule that every calculus needs, which is to close up under the structural equivalence so that the semantics is not with respect to specific syntactical forms, but with respect to the meaning of the syntax. So what we say is, suppose that P is structurally equivalent to P prime. Suppose that P prime reduces to Q prime. And finally, suppose that Q prime is structurally equivalent to Q. You can guess what this line is. We want that P reduces to Q. Yeah? Does that make sense? So that's it. Again, so I stand by my claim. This is far simpler than the pi calculus. This is the workhorse reduction rule, COM, right? And this is the only reduction rule that doesn't, see, the reason I drew this line is there's nothing up here. I have no hypotheses, right? All these other reductions have a hypothesis, right? So this is the one that gets us off the ground. Now, by the way, yes?
Just for those with category theory background, notice that here he sets up something that happens at the top level and then asserts where it can happen in smaller contexts.
Right.
In category theory, you can say what happens in a smaller context and then whisker on either side.
Yeah.
Arbitrary context, and so you have to restrict it and mark what I mean by the top context. So we'll get
Yeah.
a dual presentation of this when we get to the category theory stuff.
Yeah, absolutely. Absolutely. Yeah, so this, by the way, is the core of the Rho VM. This is, we just given the Rho VM. Now let's compare and contrast this. Lambda calculus, by the way, shares the same thing that Rho calculus shares, which is the state is the expression. So if you're looking at a Java program and you're simulating the Java program in your head, so you're a programmer, you're trying to reason about what this program does, in addition to the text that's right in front of your eyes, you must also be thinking about the stack and the heap and the threads and the yada, 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 right? Okay, so that's all implicit stuff that we all know how to simulate when we're looking through code, at least in some way, shape, or form. I don't have to do that here. There's no extra state here. I just look right at the expression, and that tells which is the state of the virtual machine. Why is that important in this context? Exactly. Exactly, right. So this is a very, very nice feature of language design to have for languages you want to stick on the blockchain. Okay, and so in many respects, this stands out as a particular core of a language. It has all of the features of the pi calculus, namely, it gives you a way to count the usage of resources like x's, which is where we can store stuff. It gives us the ability to count reduction steps. Right? So that's the complexity bit, right? And that's what we need in order to limit things with phlogiston. It gives us the ability to run things in parallel, right? So unlike the EVM, I can run these things in parallel, right? And we have a very crisp and clear notion of what a transaction is. On the other side of this, we know that the value of y is whatever the substitution was. Right? So this literally represents syntactically transaction boundaries. Right? So we have a notion of concurrency that lines up with a notion of transaction, right? So that's really, really important. Yes?
Now, we've used transaction earlier in our discussions to mean I send a message to a contract, it does a whole bunch of processing and then finishes. This is a much more restricted notion of transaction that is just synchronization on a name.
Yes. Well, it's synchronization on a name plus the corresponding update, plus the substitution. Right. So that's important when we're talking about when we're talking to the community at large. Being able to say, you know, you might have hundreds or thousands of these before you effect what you perceive of as a transaction, like, you know, updating your location on Google Maps or something. Did you want to?
So yesterday when Joe was presenting his stuff, all of his transactions started with com.
Yeah.
Presumably that's the same com as what you just wrote, right? So the question, I guess, is, were Joe's transactions the restricted version, or?
Yeah, it's exactly this. It's exactly the com events. Yeah, exactly.
Now, he had a labeled transition system, so he had to do something with the X bang, and
Yeah.
he would rewrite it to 0, but
Yeah.
it's essentially that.
Yeah. And that's why I always pound on him to say, no, you use it.
Well, you can do a lot of interesting stuff, and maybe like something that for our purposes, especially for rate limiting, that would be useful is being able to express. Being able to express something like a trace. With the labeled transition semantics, which is not presented here, and you know this is obviously cleaner than the labeled transition semantics. You can express things like sequences of actions over a set of names that you have. So my reason for doing so, or for introducing that, was that some temporal properties become simpler to specify.
So there's actually some deep stuff here that I'll just touch on and move on because we have a lot of stuff to cover. So the history, programming language semantics history, concurrency theory history. Robin first came up with CCS, which is the calculus of communicating systems. It just had the synchronization with no extra data binding. Okay? So it was a subset of pi calculus in that sense. The reason he did that was because he and Tony Hoare were thinking about modeling chips on a motherboard. So you had processors and they were connected by wires. And so the communication topology didn't change. He gets a certain way into that theory, and along comes cellular phones, and he says, oh wow, the communication topology can change. Can I adjust my theory to cover that? And so he adjusts his theory. Now CCS was given entirely in terms of labeled transition systems because it was very convenient to do so. And the reason it was convenient was because you didn't have this environment that is effectively introduced by these bindings. Okay? So once you have the environment, it's much harder to do the label transition system semantics. So Robin wanted the reduction semantics to make pi calculus like lambda calculus, right? So that this would, the problem was he didn't have a good definition of effective equivalence of processes. We haven't talked about that here, but you can see it in other places. There's a very nice effective definition of the equivalence of processes called bisimulation. Just briefly, P is bisimilar to Q if whenever P can transition by alpha to P prime. So this alpha is like a comm event or some internal comm event inside P. Then there's a corresponding Q prime that also transitions by alpha, and these two are bisimilar. So you can see what it does is it unfolds the tree, making sure that they are in lockstep with each other. Okay, so that's the effective notion. When he presented the reduction semantics, he didn't have a good way to give the bisimilarity relation because he didn't have a good notion of label. That's what Joe is talking about here, is putting the label on the transitions. So later, he comes up with barbed bisimulation, which recovers a notion of label, but it's very ad hoc. So he continues and he comes up with a category theoretic way to do this very generally. Start with a bunch of rewrite rules like this over a set of terms which are whacked out by an equivalence, and derive a set of labels such that the corresponding by simulation is a congruence, meaning you can reason equationally about process equivalence, which is important for substitutability, refactoring tools, IDE, things like that. Okay, so I have now discharged my obligations. Yes. Okay, cool. With respect to giving you the language. So we have a bunch of stuff we might want to cover. The first thing I want to talk about, and I'll just mention it briefly and give you, try to point you to the code, is we're going to modify this construct and add one other construct to make this more usable. So the first thing we want to do is we want to say for y1 from x1, yada, 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 yn from xn p. And what we want this to mean is that we wait at x1 for y1 and we wait for we wait at x2 for y2 and so on. So we have n threads, and they're all going to come together. We got to get all the results before we can start running P. Yes?
And it's not merely nesting the four individual fours. You have to get all of them or you don't get any of them.
You have to get all of them or you don't get any of them. That's exactly right.
Yeah, actually, Mike, did you want to explain how this kind of maps onto the unification semantics?
I think we don't have time to go into that right now,
Okay,
but
fair
I'd
enough.
be happy to do that later.
Yeah, sure. Okay, so the other thing we want to do is, and it turns out that you can code this idea up as using these constructions. So that makes...
Can you demonstrate that for just x1 and x2?
Yeah, so what you want to do is and by the way, this is all written down in the comments in the compiler. Okay, so what you want to do is you want to and now what we're going to do is we want to in par. Oh, sorry, this is just a P. And I'm now giving the translation of this thing. So in par, you want to wait and then there's some continuation here, and then here, and there's some continuation there, and we'll fill those in. And now the main thing is this now needs to forward, right? It needs to know that it's got something, so it has to grab a lock, right? So that's what you want to do, is you grab a lock. Oh, I'm gonna have to look at the code to make sure I get the locking discipline right. Do you have the code on the? Yeah.
I mean, this is for the select semantics, right?
No, it's for the join.
For the join, because it's okay. Well, I would. I mean, I can pull that out too. But... Can I ask you a question?
Yeah, sure.
So any of these fours with more than one parameter looks like it could be beat and erased by a for with a subset of the parameters. It's not necessarily beat, but it could be, right?
Yeah, that's correct.
Does this translation that you're starting down here at the bottom cover that case as well, so that both of the, if there are two
that's
fours and
correct.
parallels,
Yeah, that's correct.
in
Yeah.
order to wrap them
Yeah.
in this thing that will forward into a continuation,
Yeah.
the results.
Yeah.
It has to know about both of those things
Yeah.
up front
Yeah.
and be adjustable as more things arrive.
That's exactly right. That's
Okay.
exactly right. So that you're right, Kent. I was thinking about select, not the join. Yeah, you're exactly right.
I might characterize this multiple inputs in the for as saying that this is actually applicative semantics we're talking about here rather than monadic. Yes, that's. That at a later point.
Yeah, no, it's fair enough. Yeah, I understand the intuition that you're giving here. So what you do. First, let me construct the intuitions, then I'll give you the translation. So what you want is you want to turn this into a tuple, right? Effectively, your tuple looks like this. I've got a y1 and a y2, and that's sitting on the continuation. And I want to be able to fill this in multiple different ways. So I've got, in other words, we turned this into the use of the tuple space, right? So that's what's going on, right? And we want to be able to fill this in a couple of different ways. So if I get a partial match, then I record the partial match. So let's say I get the y1, so I get a z for z1 for the y1. That's the partial match, and then I know that I'm still waiting on the y2, right? Now, if I get the y2, I'm done, right? Likewise, I can have waiting in the table the z1. I'm sorry, y1, z2 for y2. Like that. And then if I get the y1, then it partially matches, right? Or it completes the partial match. That's the idea.
These are saved somewhere that any incoming process could consume.
Any incoming process, okay. That's exactly right. So that's the idea, right? And now building up the data structures for this tupling is going to take a little bit of time. So I'm just going to give you the intuition there.
Oh yeah, I don't want the full thing. I just wanted to make sure it covered the case where if you never get a y2, you can't consider that z to have been consumed yet.
That's right. Yes, that's right. So that remains. So the outputs also remain, right? So every output is also going into the table, right? The outputs are going into the table with their corresponding continuations, right?
Okay.
Yeah, does that make sense?
Yeah, no, it's fine.
And as soon as, say you've got another continuation that comes in that's waiting on only y, then it can consume the z1.
That's right.
Yeah,
That's
that
right.
was my question.
Yeah,
right.
and you want to be, so, and it turns out that there are lots of different policies that you can give there, and none of them are going to be perfectly fair. So that's something you can prove, that you will not get perfect fairness.
Right. My concern was stranding the already,
the
one that looks consumed.
Yeah,
right?
yeah, that's correct. Yeah, yeah.
I don't want that to sit in the ether
but
forever.
what that means, therefore, is you also have to go through and pick out garbage. Yeah. Yeah. Cool. Does that answer your question?
Still have some questions, but we'll discuss them.
Okay. Yeah. The important thing is that the join semantics is in our compiler is treated as primitive relative to the tuple space. And so we already have an optimized implementation for when you have multiples.
So this is primitive. So you wouldn't define it in terms of. So you wouldn't define it in terms of the single.
You can.
And parallel processes.
You absolutely can, but the way you have to do it is you have to do it in terms of tupling. Okay.
Sure.
Right. So you have to build up
tupling and
the parallel process.
Be like, well, this one could come
Exactly, exactly, that's right. And then you have, yeah, and then you have to go and erase them and then kill them off. That's exactly right. That's exactly right. So then the other one,
Greg?
yes,
Just to confirm, if a continuation queue came in that required Z sub 1, that would activate, and then the line in the tuple space that has Z1 and P would be deleted from tuple space.
that's correct. Yes.
Thank you.
Yeah. Okay, all right. So that gives you that idea. And then the other idea is, suppose I want to choose, in Erlang and a bunch of other languages, you have this idea of choosing amongst different options. So continuations that are chosen amongst a bunch of different pattern matching outputs. Okay, so in the PyCalculus notation, for people who are interested, it's prefix guarded summation. So sometimes Robin writes this, which is just willy-nilly crazy expressive. And you can prove that that's crazy expressive. Palomadici showed that if you want your translation to respect par, so that the translation of p par q is going to be equal or bisimilar to the translation of p in parallel with the translation of q, then there exists no par-preserving translation of the summation in which you have no restrictions down into one where you only have prefix guarded summation. We're only interested in prefix guarded because the other stuff is crazy expressive. Okay.
So by prefix guarded, you mean that there can be a sum under a 4?
I mean, there's a 4 on the sum is over a bunch of 4s.
Okay.
Yeah. Okay. So the next step is
Only over 4s or also over outputs?
no output summations. Yes, because then you have some non-determined. You have to flip a coin to say, send this one or this one or this one. Right? Yeah. Okay. So what we're going to do is something much more like existing languages. So I'll introduce a keyword, select, and then inside the keyword, what we offer is a bunch of comprehensions like this, and we label them out. So case, and then we just do this: y1 from x1. P1. And now I have to double index these, right? Down here. I was going to put more cases in. Don't need it because I've got the case in this. Sorry, that was like that.
Now, is the particular case that gets matched based on pattern matching, or is it non-deterministic, or how does?
In full Rholang, it's both. So you raise the other point. So this is ym1. Yn. Okay, so this is the generic form of the construct. What? No. I know. Yeah. I was hoping someone would say that. Okay, so this is the generic shape of these things, and the meaning is that you're looking for just as before, you're looking for which of these is fulfilled, right? And then whichever one is fulfilled in terms of these, so now you're keeping this tuple so you have a tuple here prefixed by one of the cases. And whichever one fills completely, you trigger that arm. Now the difficulty here, yes?
You said whichever one, but there's the possibility of multiple, and in that case, it becomes non-deterministic.
It's non-deterministic. Okay. Yeah, that's exactly right. So, and the non-determinism is race, but where the race is influenced by our policy for how we fill, right? It's not just what's coming in, but we have to do some searching to figure out when it's being filled, and this is what I meant by it's never going to be perfectly fair. There's always going to be some skew in the way we search the filling. Okay, so, and then finally, Mike has alluded to this several times. All of these here, we replace these with patterns. So you can pattern match. So you have 4, and now we put a pattern here. And this pattern is going, so when we introduce data types, so we want to add more stuff than just being able to send queues, right? And the way we add that is first by saying that all of the data is a process. So the ground terms are processes. And this lines up with all the intuition from programming language semantics, right? So when we talk about church numerals, we're encoding numbers as lambda terms. When Robin does the same trick, he encodes numbers as processes. So we're just going to follow that out. So we say all the ground types, so the numbers, strings, booleans, and so on. These are all processes. So since we can send processes, we can now send values. Now, these values, they don't necessarily have interesting patterns because we can't, except for strings, we can't really pick them apart. But we could at least test for equality. So I could do something like this. And now, P won't fire unless or until what's available at X is true, right? Similarly, if I put a 1 here, I've just said, I'm not going to go unless I get 1 on X, right? So I could implement some interesting behavior just with that, So there's a little circuit, right? It's doing something.
Strings, then you're sending in a method name.
Yeah, for example.
And the corresponding predicate process fires off.
Exactly. Okay, so that's that. But we don't just want ground data types. We want some structured data types, right? So I'd like to be able to have lists of things, right? I'd like to be able to have arrays of things or tuples of things. And then I want to be able to pattern match on that, right? So I'd like to be able to say, for X true colon R for the rest of the list from X, sorry, let's make this Y, X, P. And so now I'm not only going to fire unless I have a list that at least has this much in it, but it's got to have true at that point in the list, and it's going to produce a binding whereby Y is bound to the head and R is bound to the tail of the tail.
So this lowers via the same tuple space trick.
What?
This lowers via the same tuple space.
Oh, lowers?
Lowers, reduces to the same tuple space idea where you have.
No, it doesn't have to. You can implement pattern matching in lots of different ways.
Yeah, but in terms of semantics, it lowers to the continuations and like
Yeah. That's yeah. And so now we have patterns for all of these, and then we also have a sublanguage for arithmetic expressions and comparisons. So inside Rholang, we are able to do things like, 1 plus x, right? Or x is less than or equal to y, these kinds of things. So
are you going to be able to do matching on the structure of the process that was sent? I mean, these are all special cases for data types, the ground data types. Are you also going to have
yes.
for at p par q?
Yes,
from X?
yes, we do. We have that. We have that as well. So there's pattern matching on the structure of names. Oh, okay, cool. So there's pattern matching on the structure of names, and that introduces another one of those strange loops, right? Because then you can, since names are names of processes and processes have pattern matching, you can pattern match on pattern matches, and where does that end? Right. So we punt. There's a way in which we punt on that, which you only get a variable for the binding. You get a single variable to pattern match against that binding. And then you can pick that apart in terms of its components. Go ahead.
Is there some piece of syntax that tells your pattern match that you're doing an equality match as opposed to binding a variable? Like, for example, your true there. How do I know that true isn't just the name of some other variable I want to bind?
Because true is a keyword.
True is a keyword. Okay. So then can I only pattern match equality on keywords? Like if I had...
You can only pattern match equality on ground values.
Okay.
Yeah.
Okay, so like in Scala, for example, you have the backticks that let you.
Yeah,
but that's
we
not a
don't
thing.
have that feature yet.
Okay.
Yeah.
Cool. So one point of ambiguity I can see here is if y is bound outside of that for expression there, that y is already bound to something.
This shadows.
So it shadows.
It always shadows, just like in Scala. Yeah. And then.
Now, there's another place that we've got conditionals. So you've got your sequence of joins and then if condition on all of the resulting values.
So there's
one way of implementing this could be just bind them all and then have the pattern match in the conditional.
Yeah, you could yeah, that's an approach. But that raises another piece of syntax I just wanted to touch on briefly. So since we have pattern matching, it becomes very nice to be able to just say match, so just like in OCaml or Scala. Scala puts the thing on the left side of the match. We chose the OCaml style. So match, and now we can put a value here, but let's, put a P here since. So match P with, and now you can do case, and that's a pattern, and there's your continuation. So that's, does that make sense?
So are those patterns restricted to the ground terms again?
No,
or?
it's the pattern matching that we've been describing in general.
Okay, so you couldn't say match P with Q par R.
Yeah.
Because then there's no obvious way to factor it, even if it can be.
Exactly. Yeah, exactly. So it's just restricted to so for purposes of this discussion, treat this as if it were a value. So we've introduced the syntactic category value, and yeah.
So match is just syntactic sugar for select?
Yes, you can implement it in terms of select. That's exactly right. And that covers the untyped syntax, unless I've missed something. Have I missed anything?
Nothing
Okay.
major.
So do people feel like they have a sense of the language?
There's also the sequential arrow.
Right. So are we gonna? So we're
out of time, but there is the sequential arrow. There's the notion of collections in the X position. There
right.
Are
yeah.
various
Exactly.
other things.
So there are some features that we are currently nailing down for Mercury. In particular, what we want to do is to enable people to plug into the for comprehension syntax. And what do they have to do in order to implement a widget that can plug into the for comprehension syntax. So this is like in Scala implementing the monadic filter interface. Or in Haskell, there's, you know.
Did you want to mention RChain quickly?
Oh, okay, sure. We can do that very quickly. So you may be asking yourselves, you may find yourself, you may be asking yourself, all right, so how do I do user-defined data types? And it turns out that there's a quick and dirty implementation of JSON in Rholang, right? So suppose I have some JSON object. So I've got my key. So there's my JSON. And how do I turn that? And Mike has already given you, I think, the... just a subset. Yeah. Okay. So then I'm now... And, you know, I've been using this notation a lot. In programming language semantics, the double braces is conventional for meaning of, right? So you can think of this as compile this down to, right? So that's that, and this becomes a nice notation in terms of writing these things. It's a very convenient notation, so that's why I use it. So this is going to be equal to go and translate the key, figure out whatever that is, and in fact, if this is the binary form, then the in-array form of this I will write like that. Does that make sense? People tracking there? This is just the in-array form of the binary form. Okay, so then I can do this.
And the interpretation of the key, since it has to be a string in JSON, is going to be a string in RChain. Yeah.
Right, exactly. But what you really want, if you're going to do a bang here, right, what you really want, if you want to preserve it, this has to be a name. Right.
String.
Yeah. So if this is the string k, then, and that is the number 5. Then I get at k colon and then 5. Bang, sorry. That's how you do the translation. I don't. No, you don't have to replicate that, because when this gets communicated over to the other side, it's a name. It's a name, right? Unless I dereference it, and then it becomes a process. Right, and so that has some really nice properties, right? Because if you dereference it, it's literally the act of storing those values in those names, right? So the structural representation is equal to the operational representation. They're perfectly mirrored.
So if there were process structure-based matching rather than merely these patterns, I can see how to pick apart the name and extract the individual pieces.
That's right. Name structure. You can also, the thing is you do name structure picking apart.
Okay, so that just hadn't been.
Yeah. Yeah, sorry, I just mentioned it, but I didn't write it down. Yeah.
Great. I think we're out of time.
We're out of time, so thank you very much. Maybe take just a couple of questions, just in case. Any other questions, thoughts, comments? If you want to see real-world examples of Rholang in operation, Kent has made a nice video walking through the ERC20 contract, and it's in GitHub. And you have an auction contract? No, that's what I'm working on. Okay, all right. Do you have drafts? Sure. Okay. All right. Are they in GitHub? Well, I haven't pushed them yet. Okay. All right.